CML is still up. Yep, CML is still up. All right, so we're gonna jump into. I am totally in the stinking way over here. I'm shrinking. All right. I'm so small now. All right. Let's jump into it, guys. So, chapter 1. So, what we'll do is we're gonna review chapter 1 real quick. All right. And then we're gonna go over the do I know this already type quiz. So again, this is fundamental, guys. Chapter 1. This is the CCNA 200.300 official cert guidebook. So this is this book right here. Let me get this in the camera view. So this exact same book right here. This is just off of O'Reilly. This is my O'Reilly description here. And what I've been thinking, I've had this description for quite some time. And what I've been thinking is maybe this might be a better way for me to kind of, you know, as you guys are watching this, while you guys are joining the stream with me, this would be a way to, you know, to introduce the actual, the sources that I'm getting this information from, guys. All right. So we're gonna do a quick review. I'm gonna go over the "Do I know this already?" quiz, and then we're just gonna go right down the line, and we're gonna review the chapter. It shouldn't take us too long. So, chapter 1, the introduction to TCP/ICP networking. What this chapter is going to cover is network fundamentals, comparing physical interfaces and cabling types, single mode fiber and multi-mode fiber, copper, and then multi-mode fiber optics, pretty much fiber optic cabling, connections, Ethernet, shared media, or point to point. All right. What I'll do is I will have let me turn this up so I can actually hear it correctly.
Welcome to the first chapter in your study for CCNA. This chapter begins part 1, which focuses on the basics of networking. Networks work correctly because the various devices and software follow the rules. Those rules come in the form of standards and protocols, which are agreements of a particular part of how a network should work. However, the sheer number of standards and protocols available can make it difficult for the average network engineer to think about and work with networks, so the world of networking has used several networking models over time. Networking models define a structure and different categories, layers, of standards and protocols. As new standards and protocols emerge over time, networkers can think of those new details in the context of a working model. You can think of a networking model as you think of a set of architectural plans for building a house. A lot of different people work on building your house, such as framers, electricians, bricklayers, painters, and so on. The blueprint helps ensure that all the different pieces of the house work together as a whole. Similarly, the people who make networking products and the people who use those products to build their own computer networks follow a particular networking model. That networking model defines rules about how each part of the network should work, as well as how the parts should work together so that the entire network functions correctly. Today, TCP/IP rules as the most pervasive networking model in use. You can find support for TCP/IP on practically every computer operating system, OS, in existence today, from mobile phones to mainframe computers. Every network built using Cisco products today supports TCP/IP. And not surprisingly, the CCNA exam focuses heavily on TCP/IP. This chapter uses TCP/IP for one of its main purposes, to present various concepts about networking using the context of the different roles and functions in the TCP/IP model.
So again, this is the this is the introduction to the TCP model, and very important information as we start our journey back into networking. Okay, so we'll start right here, guys. We'll start with a couple of these questions. I believe there's about 7 of these questions. So which of the following protocols are examples of the TCP/IP transport layer model? All right, so transport layer. We want to remember that in the TCP/IP model, it's different than the OSPF. Am I saying that right? OSPF model? Yeah, it's different than the OS. So in the TCP/IP model, there's 5 layers. Okay. All right. On the very bottom layer, that's where you have. So this would be like your link layer, or the cabling. This is where the actual you can actually think of like the copper wiring and the information going over that. Okay. On the second layer, all right. Yeah, I'm going over that, right? Right. Come on, Joe. Use your head. On the buy followers. There we go. Sure. Look at that. I got a second person in the stream. Not buying followers. So the next layer above layer 1, that is yeah, you got layer 2, which is your data. Now I'm just trying to go this all off memory. Data IP address, transport, yeah. And then is it application? Is it app? I might mess up the names. But if you could think, so this is pretty much where the MAC addressing is. This is right here. What's the other name for the IP layer? That would be the networking layer. And that's where all the IP addressing and all that happens. Transportation layer. These are your protocols. So like TCP/IP and all that. And then this is like session. Hold on, let me just make sure I'm going up. So let's just go over question number 1. So we're gonna say question number 1. We're gonna say choose two answers. We're gonna say TCP and UDP. All right. Let me just erase all this and we pull out this. We're gonna say for question 1. We're gonna say D and F. All right, for question number 1. All right. All right. Question number 2. So question number 2. Which of the following protocols are TCP/IP data link layer protocols? Okay. Data link layer. All right. So if we're thinking data link, and what we got? Choose 2 answers. I am thinking point to point and Ethernet. Yeah, because HTTP that would be in the that would be in the session. That would be in the top session layer. Okay. IP again, that's in the networking layer. All right. UDP and TCP, that's UDP and TCP, that's in the just went over that. Yeah, that's in the transport layer. So UDP, and TCP transportate. All right, that's how that's the transportation protocol. And then SMTP, and yeah, that's the last one. SMTP, that actually fall into SMTP, that'll fall into the session layer as well. So SMTP, that falls into the session layer as well. So the only two things we have left is Ethernet and PPP. Okay, so let's come over here. Just erase these two. Say, whoa, too small, too big. And Goldilocks over here. All right, we're going to say question 2. I'm going to say B and G. All right. Let's go down to number 3 now. The process of HTTP asking TCP to send some data and making sure that it receives correctly is an example of what? Okay. So again, here we go. Draw it back up. So just like I had on the board, just again, HTTP is top layer. Okay, so that's layer 5. All right, layer 5 session. All right, TCP is the layer just underneath that. Okay, in the transportation layer. Okay. All right. So that would be adjacent layer interaction. Okay, adjacent layer interaction. All right. Again, let's find out. So let's write that answer right here. So 3, we're gonna say B, right? Let's go to the next one now. 4, the process of TCP on one computer marking a TCP segment on segment 1 and receiving computer, then and then the receiving computer acknowledging the receipt of TCP segment 1 is an example of TCP talking to TCP. I mean, just think logically, not B, A. For which one? Which one are you talking about? You gotta give me some context. Which one, Fuzzy Mogul? Which one? Tell me. Where did I go wrong? Two? Oh, yeah, you're right. You're right. Yeah. You're right. I was saying Ethernet 2 the whole time. You're exactly right. I put that by accident. So it's A and G. You're right. You the man. And then we're on 4 now. And then 4, that would be, let's go down to 4. Whoa. Boop, boop. Stop it. 4, TCP, talking to TCP, same layer interaction. We're going to say B on that one too. So 4B. All right. Hello, all I know. I must have got my brain mixed up. All right. So the next one, question 5. The process of a web server adding a TCP header to the context of a web page, followed by adding an IP header and then asking a data link header, and then adding a data link header and trail is an example of what? So it's not same layer interaction. It's not the OSI model, and it's not all the answers above. So the only one we got left is data encapsulation. Okay, so this is the process in which data is encapsulated to send through the transportation model. Again, we're going down the chain. We're going down the chain to the final level, which is obviously the wire, which is going from one device to another device. Okay, so in that process, it's encapsulating all of that data. All right. So what we're gonna say for number 5 would be A. All right. All right. 6. Which of the following terms is used specifically to identify the entity created by encapsulating data inside of a data link header and trailer? All right. So, data link. All right. So, data link layer. So, a data link layer, it's not a segment. Segment is transportation. We know that. All right. Frame could be frame. All right. I believe it is frame. Packet, so IP packet. So IP packet, you're thinking networking layer. Okay. So I'm going to do a process of elimination and not say chunk. I'm going to say it is D, frame. All right. Let's go with D. We're going to find out if we're right. So 6, we're going to go with frame. So D. All right. Which OSI encapsulation term can be used instead of the term frame? All right. Again, it almost just answered itself on the last question, and that would be a layer 2 PDU. Okay. I believe. We'll find out. Let's gonna say 7. All right, let's find out how good we did, guys. So, woo, I totally skipped it. All right, so we got, let's see what we got right. So, number 1, DNF, we did good. Number 2, A and G. Thank you, Fuzzy Boogle, for correcting me. All right, number 3, B and B. 4, B. All right, number 5, A. Number 6, D, and number 7, B, and B. All right, we did pretty well, guys. I'm actually pretty happy. And I promise you, I did not do a review before I did this either. I promise you I didn't. I really didn't. All right, cleaning my board up real quick. All right. Cool. All right. All right. So that was pretty good. That was a good quick review. Now, it's a pretty long chapter, but we're gonna kind of like breeze. We'll kind of breeze. We'll kind of like touch on some things, and breeze through it. Okay. So perspectives of networking. So if you're new to networking, like many people, your perspective of a network might be that of a user. All right. Like most people, like I was before I got into this. All right. I did not know. All I knew was I grab my phone, I go onto the internet, and I go onto the web page I want to go on. That's all I knew before. All right. But there's a whole lot of jazz and business that goes behind that. Okay. As opposed to the network engineer who builds networks. For some, your view of a networking might be based on how you use the internet, from home or using high-speed internet, connecting like digital subscriber, like DSL, digital subscriber line, and cable TV. All right. Pretty much, this is just showing you a simple, easy breezy type network design. All right. Now, like I said, we'll create a lab too, guys. In the area of which this chapter is covering. Okay, very basic. Okay. All right, it'd be from the very high. We'll do a high level type lab. We won't go too crazy. end user perspective on high-speed internet connection. The top part figures shows a high-speed internet user. The PC connects to the modem. The modem connects to a cable that's on your wall. It's your internet service provider, your ISP. That they've pretty much, for most modern houses these days, you got a wireless router that you purchased off of Comcast, Verizon, Dish Network, whoever. They've supplied you with a router, and all you do is you jump on your laptop, you jump on your phone, you put in your Wi-Fi password, and wham bam, thank you ma'am, you're connected to the internet. You don't care about your IP address, you don't care about anything like that. All you care about is getting onto the internet. That's it. That's all you have to care about. And that's where all that steps that you don't have to take is what has already been configured and supplied to by the internet service provider. And it's from the people that created all these protocols that have made it so easy for you to get on the internet. Now, if you're about my age, and I'm about 35 years old, you can still remember before the internet was popular. Now, the internet was existed by the time I was born, but it wasn't popular. Like, I wasn't born into a household that had internet. We got the internet when I was probably, I don't know, about 9 or 10 years old. I believe that's when we got the internet. Maybe a little older. But it wasn't till, again, I didn't grow up knowing exactly, what it was. I didn't just jump on a computer. We had, I believe when I was very young, we might have had one of those old Mac, one of those old OG Mac computers that played. Man, it was one of those legit floppy, not floppy disks like if you can even remember a floppy, but it was the legit old school floppies. And that's what it. Let me see. Yeah, it was a phone line. Yeah. It was I think what was it? AOL first. When you plugged in to the computer, and then it gave you that god awful sound. And then it took 10 years. It took 10 years to just get on the internet. Good luck trying to download, whatever, or send a message. Things have changed real fast. And there's still, the speed of that change has even picked up even greater. And the fastness of things are even getting more, faster and faster as things progress, all right? So we'll continue on down here. Users of an enterprise network might have some idea of how the network in their company or school works. People realize that the network, you realize that they use the network for tasks. So from sending emails to using your cash register to a multiple array of what we do these days. A lot of these programs and everything that we do now, they're all, now for the most part, a lot of things are web-based applications, and within the next couple of years, everything's going to be a web-based application. Web-based is obviously the way everything's going to be. So the workload, the load on the internet is going to continue to get greater and greater and greater. So it's up to network engineers and internet service providers, American AOL. You had to call them to access the internet. Oh boy, I'm glad I really don't remember those days. Like I said, I was real young back on those days. Man, times have changed. So yeah, like I'm saying, the things now are being better. More. The internet's being used more and more every day now. All right. We'll go down here to the Tcip networking model. A network model sometimes also called a networking architect or networking blueprint refers to a comprehensive set of documentations. Individuals, each document describe one small function of a network. Collectively, these documents define everything that should happen for a computer network to work. Some documents define protocols, which in set of a logical, sets of logical rules that define that devices must follow to communicate. So everything's about communication, and everything has to follow the same rules. If things ain't following the same rules, then it's the wild, wild west. And that's how things used to be too. And it's going to continue. It's going to get into that. You can think of a network model as an architect blueprint for building a house. Same thing. All right. Sure, you can build a house without a blueprint. However, the blueprint ensures that the house has the right foundation structure so that it won't fall down. It has the correct hidden spaces to accommodate for plumbing, electricity, gas, so on, and also many different people that are going to work on that house all have to follow that same type of rule as well. Thank you very much for that. I like that. Yep. Yep. That is an awesome picture. Thank you very much for that. Thank you. Fantasy Mogul, you the best. So to continue on, the networking model again is, you can think about it as how you would develop your house. Now, I was in the construction field for a better half of my life, and I was a sheetrocker. I was a framer, and so on and so forth. I could only get on the job in certain steps, in certain phases of the job. I couldn't just per se jump in before the plumbers and the electrician got in. Because if I started laying sheetrock inside of that apartment or house that I was building at the time, what would happen was the plumbers and the electrician, they wouldn't care. They would just start punching holes in my newly sheetrocked and plastered walls, and I would have to go back and redo everything all over again. You can think about networking in a similar fashion, all right, where certain things have to be done in certain stages and in sequences, so that way it all works together. And what this is leading up to, and the history of leading to the Tcip model, is before, and I believe this is where it's going to talk about, IBM here. Before Tcip was the actual quote unquote model forever now, you had the OSI model. All right, so OSI. All right. And there was other, and it shows you down here in the description, right here, it starts talking about how other vendors, before, here we go. So yeah, before in the 80s, you had IBM, you had, whoever else over here, and you had, Tom, and you had Jerry, and Sally Q, whatever. Each one of these companies in the beginning, brilliant, smart, super smart people, but they weren't working together, and they were creating their own, models per se for their own, networks and whatnot, because there wasn't a set standard just yet. And IBM, I believe, it was IBM as it stated here. For example, IBM, one of the largest company, here. Let me just do it this way. It'd be easier.
Model. Do I know this already?
Stop it.
For example, IBM, the computer company with the largest... Not always been so simple. For example, IBM, the computer company with the largest market share in many markets back in the 1970s and 1980s, published its Systems Network Architecture, SNA, networking model in 1974. Other vendors also created their own proprietary networking models. As a result, if your company bought computers from 3 vendors, network engineers often had to create 3 different networks based on the networking models created by each company, and then somehow connect those networks, making the combined networks much more complex. The left side of figure 1 to 3 shows the general idea.
So as I kind of just described right there, it was the Wild Wild West before, all right? And then as things continue to develop, it gets into the OSI model, the Open System Intercommunication, all right? Now that was being developed, states it all right here. Yeah, we'll come down right over here.
Idea of what a company's enterprise network might have looked like back in the 1980s, before TCP/IP became common in enterprise internetworks. Figure 1 to 3 historical progression, proprietary models to the open TCP/IP model. Although vendor-defined proprietary networking models often worked well, having an open, vendor-neutral networking model would aid competition and reduce complexity. The International Organization for Standardization,
So the ISO
took on the task to create such a model, starting as early as the late 1970s, beginning work on what would become known as the Open Systems Interconnection, OSI, networking model. ISO had a noble goal for the OSI model, to standardize data networking protocols to allow communication among all computers across the entire planet. ISO worked toward this ambitious and noble goal, with participants from most of the technologically developed nations on Earth participating in the process. A second, less formal effort to create an open, vendor-neutral, public networking model sprouted forth from a U.S. Department of Defense (DoD) contract. Researchers at various universities volunteered to help further develop the protocols surrounding the original DoD work. These efforts resulted in a competing open networking model called TCP/IP. During the 1990s, companies began adding OSI, TCP/IP, or both to their enterprise networks. However, by the end of the 1990s, TCP/IP had become the common choice, and OSI fell away. The center part of figure 1 to 3 shows the general idea behind enterprise networks in that decade.
All right. So, as things developed, as time persists in companies, they were slowly looking for better solutions. Instead of having to deal with the Wild Wild West, the ISO developed the OSI model. Okay, and again, they were going after what is today. It's in the TCP/IP model, and you will see is nearly similar and uses the TCP/IP model. Still uses some of the same terminology in the OSI model. It's almost like, you know, it took the market and then it kind of like took some of that stuff that the OSI model was going after to kind of keep things in a similar fashion. And you're gonna see where the 7-layer OSI model and then the 5-layer TCP IP model. Okay, now you're gonna still see the 7-layer terminology used in the 5-layer terminology. Okay, it's gonna confuse you because the TCP/IP model kept that 7-layer terminology, and that represents the higher level functions, the app functions. Okay, and if you've used Wireshark and stuff like that, you have seen the 7-layer. It doesn't exist in the TCP model, but the TCP model still uses the 7-layer terminology, even though it only states that it's a 5-layer model. Okay, so let's continue on. So where are we at? So here in the 21st century, TCP model dominates, but they have overview. The TCP model defines the reference of a large collection of protocols that allows computers to communicate. They define the TCP model. Use documentations called RFC, request for comments. Okay, so when you see the terminology RFC, it's stating request for comments. All right, so this is, and then the IEEE. So the IEEE, the engineering, the Institute for Electronic and Electrical electronic engineers, the IEEE, they are they're the go-to source for the standard. All right, they create the standard for pretty much everything that comes with electricity, networking, anything that has to do with sending something through a cable or fiber optic or anything like that. The IEEE has created a standard for it. Okay, all right, and they use what it's called an RFC. Okay, a request for comments. All right, so that's where you're going to see a request for comments like RFC 1918. All right, RFC 1918. I have that on my wall because that's a very, 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 very important one. Where's all my RFCs that I had on my board? That's what I get for taking down, cleaning up my walls. I had a whole list of RFCs on my walls, but I believe one of the main ones is RFC 1918. That's neither. We'll get into that all that. All right. So, as we continue, yeah. So here we go. So here right here, like I was just going over. This is the 5-layer TCP IP model. Right there, you got physical, data link, network, transportation, and application. Okay, but again, inside of the TCP model, they still will use the 7-layer terminology, and that's gonna look like boop. But I did it anyways. All right, we'll keep going. All right. The TCP model shows the more common terms and layers used when people talk about the TCP model today. The top layer focuses on the top layer focus on transporting. The top layer focuses on the transporting of bits over the individual link. The data link layer focuses on sending the data over the physical link. For instance, the network uses different data link protocols from Ethernet LANs versus wireless LAN, so Wi-Fi versus cabling. Okay, the network layer focuses on delivering data over the entire path of the original sending computer to its final destination computer, and the top layer focuses on the application. All right, so HTTP, HTTPS, SSH, SMTP, and so on and so forth. Okay, so a slightly different 4-layer. Yeah, we're not going to get into that. Just confusing more people. The TCP model has gone through a couple different changes, but it's finally resonated on the 5-layer. Okay, and here's the kind of like quick breakdown. So the application, HTTP, POP3, SMTP, you got SSH in there, and a couple other ones. Transportation, you got TCP and UTP. All right, the IP or a network, you get IP or ICMP. And then you have on the very bottom data and physical link, Ethernet, and then it gets into Ethernet, Wi-Fi, and then the actual IEEE standards, the 802.11. All right, the TCP/IP application layer, so the very top. All right, layer protocols provide services to application software running on a computer. The application layer does not define the application itself. Okay, remember that. The application layer does not define the application itself, all right? But it defines the service that the application needs, okay? So HTTP, HTTPS, that's how you're gonna get your web browser. It doesn't define the actual, the web browser itself, all right? It defines the protocol that it's going to use to get you that web browser, okay? For example, application protocol, HTTP, defines how a web browser pulls context from a web page from a web server. In short, the application layer provides the interface between software running on the computer and the network itself. All right. Arguably, the most popular TCP/IP model application today is the web browser. Again, everything is slowly, even software is slowly starting to become web-based. All right. Here shortly, instead of downloading programs, you're going to be just logging into an internet server, and then there you go. Then you're going to be using, software as a service from there, and then they're going to charge you whatever they want to charge you. Oh yeah. Oh, thank you. Thank you. That's why I had RFC 19 so stuck in my head. Is it's from that. Yep. Yep. Thank you very much, folks. You are awesome. So HTTP overview. What really happens to allow the web page to appear on your web browser? Imagine Bob. Everybody loves Bob. All right. Opens his web browser. His web browser has a configured to automatically ask for a web page off of Larry's server. All right, as the default home page. All right, the logic's like this: give me your web page. Here's the web HTML file. Obviously, there's a little bit more that goes behind that, but that's pretty much my computer is requesting that web page from, saying I want to get to Google, and the second I open up my web browser, it's automatically going to be requesting that page from Google, and then Google gets that request and then sends me that web page. Okay, that web page is just not automatically on your computer. All right, or it just doesn't get sent to you. You have to request it. So there's a request involved in a lot of these things. All right. All right. So what really happens? Bob initially asks Larry to send his homepage back to Bob. Larry's web server software has been configured to know that the default page is contained in a file called home HTML or whole, HTML, whatever. Bob receives the file from Larry and displays the content on Bob's web browser window. All right. The HTTP protocol mechanism. Taking a closer look, this example shows how an application on each endpoint computer specifies the web browser application and web server application. Uses a TCP/IP application layer to make the request for the web page to return the contents of the web page. The application uses the Hypertransfer Protocol, HTTP. All right, Hypertext Transfer Protocol. All right, that's where the HTTP comes from. All right, HTTP didn't exist until, here's a very important name. All right, Tim Berners-Lee. All right, he made the first web browser. All right, very important. All right, created the first web browser and the web server in the early 1990s. Woo! I was alive back then. All right, Berners-Lee gave HTTP functionality to ask for contents of a web page, specifically by giving the web browser the ability to request a file from a server and giving the server a way to return the content of those files. The overall logic matches what shows on figure 1.5. All right, so here is the actual logic. The request, the header. Okay, I want to get that, so your get request. Okay, so those who start messing with APIs, the get, all right, the get request, and then sends back, here it is, all right, here's the header, it's okay, there's the data, and then obviously it sends it in fragmentations too, all right, but that's neither here or there. Okay, well, we'll get into that later as we continue on. All right, so we're gonna keep going down the transportation layer. Although many TCP application layers protocols exist, the transportation layer includes a smaller number of protocols. The two most commonly used transportation protocols are the transmission control protocols, TCP, and the user datagram protocol, UDP. All right. Transport layer protocols provide services to the application layer protocols that reside one layer higher in the Tcip model. How does the transport layer protocol provide a service to a higher layer? protocol. That's it. This section includes that general concept. Okay. All right. All right. TCP/IP recovery basic. All right. So TCP is reliable. UDP is not reliable. Okay. It's going to go into that. So to appreciate what the transport layer protocol does, you might think about a layer above the transport layer, the application layer. Why? Keep going down. So, for example, Bob and Larry uses HTTP to transfer the home page from the web server Larry to Bob's web browser. But what would happen if Bob's HTTP GET request had been lost in transit through the TCP network? Or what had happened if Larry's response, which included the context of the home page, had been lost? Well, you might expect in either case that the page would not show on Bob's web browser. Okay. The TCP needs a mechanism to guarantee delivery. Okay, guarantee delivery of data across the network. Because many application layer protocols probably want a way to guarantee delivery of data across the network. The creators of TCP included an error recovery feature. To recover from errors, TCP uses the concept of acknowledgement. The acknowledgement. All right, very important. All right, this basic outline behind how TCP notices lost data and asks the sender to try again. All right, so after Bob's web browser has already sent the initial GET request, all right, this is where TCP comes in. So TCP, we're still talking about TCP. We haven't talked about UDP yet, okay? So here we go. It sent its first packet. First packet went through. Second packet, lost, all right? But then it sends another, it continuously sends these packets, all right? The third packet, it gets the third packet, okay? Now, Bob's web browser saw that it didn't get the second actual packet. So it's going to send a request for that second packet, okay? And that's how the TCP model, the TCP protocol works, all right? All right. So continues to talk about that and same layer interactions. So here's some key topics for us to remember. So same layer interactions on different computers. The two computers use the protocols to communicate with the same layer on another computer. The protocols define a header that communicates with each other, which with each computer wants to do. Adjacent layer interactions on the same computer. On a single computer, one lower layer provides a service to a layer just above it. The software and hardware that implements the higher layer requests the next layer perform the needed function. Okay, so it talks about the TCP layer, the network layer. So again, we're slowly coming down that 5-layer ladder now. Okay, the application needs includes many protocols. The transportation layer includes further, and most noticeably the TCP and UDP. The TCP network layer includes a small number of protocols, but only one major protocol, IP, the Internet Protocol, all right? IP, so IP addressing, and stuff like that, all right? In fact, the name TCP, so Transmission Control Protocol, and IP, Internet Protocol, that's where the TCP model got its name from, all right? It's simply the names of the two most common protocols, okay? Separated by a slash. Woo, man, they worked hard on that name, all right? IP provides similar features, most importantly, addressing and routing. You won't be able to communicate on a network without an IP address, okay? Very important, all right? This section begins with comparing IP addressing and routing with another commonly known system that uses addressing and routing, the Postal Service, all right? Just like you can't get mail without an address, woo! Following that, this section introduces IP addresses and routing. Yep. So, here.
Imagine that you just wrote 2 letters, one to a friend on the other side of the country, and one to a friend on the other side of town. You address the envelopes and put on the stamps, so both are ready to give to the postal service. Is there much difference in how you treat each letter? Not really. Typically, you would just put them in the same mailbox and expect the postal service to deliver both letters. The postal service, however, must think about each letter separately and then make a decision of where to send each letter so that it is delivered. For the letter sent across town, the people in the local post office probably just need to put the letter on another truck. For the letter that needs to go across the country, the postal service sends the letter to another post office, then another, and so on, until the letter gets delivered across the country. At each post office, the postal service must process the letter and choose where to send it next. To make it all work, the postal service has regular routes for small trucks, large trucks, planes, boats, and so on, to move letters between postal service sites. The service must be able to receive and forward the letters, and it must make good decisions about where to send each letter next, as shown in figure 1 to 8.
So if you're thinking about how the postal service works with addressing and physical routes, I'm talking physical routes, streets, highways, plane, trains, automobiles, it is nearly similar to how a internet network works, okay? It has an established, the postal service has an established routes that it knows if I need to get here, I have an established route to get there. If I need to get all the way over here, I have some routes, I have an array of routes that I can take, but I need to get the most efficient route so I can get there, so I can get that package delivered to where it needs to be. But it all needs addressing. It all starts with addressing, okay? You can't have the same address as local Bob over here and have the same address as California Bob over here. It does not work like that, all right? In how it, you can, that's where we're going to be later on discussing how private addressing versus global addressing and how that works, and the difference between how, these are later subjects, but how your router changes your inside local addressing and then turns it into a global routable addressing when you actually go on the internet. So your phone, so say if you look at your phone right now and you're hooked up to your own home Wi-Fi, you're going to see an address most likely of 192.168.0. Probably 105 or 10 something like that. Whatever your DHCP server on your router has assigned your phone, but it's going to be 192.168. Something. All right, guaranteed. Most than likely. All right. That address though is not globally routable. You can't just route to the actual internet with that address, because that address is a private address. You can talk to your computers in your own home network with that address, okay? But you're not going to be able to talk to Google per se with that address, okay? That's where your router is going to change your address, and that's another subject, into a global address, okay? All right. Internet protocol address basics. All right. The IP defines addressing for several reasons, for important reasons, okay? First, each address that uses TCP/IP, each TCP/IP host needs a unique address so that it can be identified in the network. IP also defines how group addressing together, okay? Just as the postal system groups addresses based on postal code, so you have a postal code, all right, wherever you live, no matter where are you in the world, you have a postal code, okay? Like your zip code in the United States. To understand the basics, which shows the familiar web server. So it's showing Larry and Bob all over again. So you have Mr. Larry, you got Bob over here, you got Mr. Archie over here. Larry's web server is at 1.1.1.1, Bob's at 2.2.2, and Archie's at 3.3.3, okay? They all needed a unique identifying address so they can all communicate with each other, okay? And we're going to make a small little lab too here very shortly to just go over that, okay? All right. So IP routing basics. The Ccip model network layer uses IP protocol provided a service for forwarding IP packets from one device to another. Another device with an IP address any device with an IP address can connect to the TCP network and send packets. This section shows the IP routing example from perspective. All right. Note, the term IP host refers to any device, regardless of size, power, and whatnot, that has an IP address and connects to them to the TCP network. Okay, so any device. All right. So if your toaster has an IP address on it, it's an IP host. Okay, it's a host. All right. Pretty soon your toasters will have IP addresses on it. I promise you. All right. All right. You're gonna have a smart toasters here soon. So what's yep. So this figure it shows same similar type concept, basic routing example. Okay. Yep. So now we're taking those steps down. We're taking the steps down. Now we're in the physical layer. The TCP model data link and physical layer defines the protocol and hardware required to deliver data across a physical network. Okay, now we're getting to cabling and whatnot. All right, the two networks to work, the two work together quite closely. In fact, some standards define both the data link and physical layer functions. The physical layer defines the cabling and energy for example, the electrical signals. So in your cabling, in your house or in your home office network, there's an electrical signal that's going through those wires. Okay, that's communicating out. That's how this all stuff works. Okay, that flows across the cables. Some rules and conventions exist when sending data over the cables. However, those rules exist in the data link layer of the CCIP model. Focusing on the data link layer for a moment, just like every layer in the network, the TCIP data link layer provides a service to the layer above. So it's always each layer is providing a service to the next layer. The top service cannot perform anything without the lower adjacent layer performing its duties. It just won't work. Okay. Focus on the data link layer. All right. Focus on the data link layer for a moment. Just like every other layer in the network model, the TCP provides a service to the layer above in the model. When a host router IP processes choose to send an IP packet to another router or host, that host or router then uses the link layer details to send the packet to the next host. So you have your networking layer. It's gonna send data down to the data link layer. That's gonna send it to the physical layer. It's gonna send it through the wire. That's gonna go to the other computers. First physical layer, data link layer, then the networking layer, and then the TCP, and then all the way up. Okay, we're just climbing up and down ladders. All right. Because each layer provides a service to the layer above it, take a moment to think about the IP logic related in figure.10. Okay. So again, it's taken from the network layer. It's going to go down. It's going to be encapsulated. That's a tough word for me. To the data link layer, it's going to go through the actual, it's going to go through the actual physical wire. All right. And again, it's going to arrive at the other side at their data link layer. Then it's going to go up to the network layer. Okay. All right. Yep, pretty much exactly what we just went over. Data encapsulation. All right. Yep. That's just going over the encapsulation of how the data is. It's pretty much as the information's coming down, it's being each layer is adding a header and a layer to that actual packet. Okay. All right, and here's how the encapsulation. There we go. Woo, spit it out. Of your actual data. Okay. So segment, packet, frame. Boom. Segment, packet, frame. Say it again. Segment, packet, frame. One more time. Segment, packet, frame. Transportation, network, data. There we go. OSI model terminology. Again, so this is where it gets into where it talks about comparing, some of the similarities between the OSI model and the TCP model, and how the TCP model took some of that same terminology into itself. Okay. All right, and here we go. So right here, this is a great example of exactly what I was talking about. So key topic to remember. Okay, so in the fifth layer on the TCP/IP model, that's the application. But over here on the OSI model, it gets broken down into 3 separate layers. It's session, presentation, application. Now, again, if you've used packet capture software like Wireshark or whatnot, you are still going to see that it is still represented as the layer 7. Okay, it still represents the application like the HTTP and all that as the 7-layer application. Okay, so it still uses that same terminologies. All right. All right. Now it's just going over on how the OSI model encapsulated its data. Okay, and these PDUs still exist. Now again, this goes back to, this is where things still get a little confusing because of how TCP incorporated the OSI terminology, and it still uses this terminology inside of its own protocols. Okay, and again, it's just, once you get over the fact that you understand that it took some of that terminology, it'll be easy to understand. So again, it's just going over that. And now how'd we do? Hey, look at that. We've gotten to the end of the chapter. Woo! We did it. So some key terms to note, guys. So we have a JSON layer, interactions, man, my speech impediment is awful. Encapsulation. Man, I gotta get better at that. So we have de-encapsulation, encapsulation, de-encapsulation, a frame, network model, packet, PDU, protocol data unit, same layer, interaction, segment. All right. So, like I promised, we'll go right over here, and I'm just gonna blast up a new lab. So CCNA chat 1. All right. I'm just gonna grab too simple. We're gonna make a real simple network, guys. Okay, this is as simple as a network's gonna be. All right. You're gonna be Bob. Hi, Bob. You're going to be Larry. Hi, Larry. All right, we're going to connect Bob to Mr. Larry. Let's fire Bob and Larry up. This shouldn't take too long. Come on, Bobby. All right. Bob's up. Come on, Larry. Hurry up. This up a little bit. Cisco. All right. We're gonna add. Let's add an IP address. IP. 10.0.0.1/24. All right, I'll go over to Larry now. Give Larry an IP address real quick. All right, now we'll go back over to Bob. Now, Bob, let's go talk to Larry. All right, there we go, guys. Bob's talking to Larry. Now, to get back to addressing and why addressing is very important, and I know we didn't really cover this, but say I gave Bob an address outside of Larry's zip code. Okay, there's no router in this network. We don't have any other devices. It's just a simple cable to cable network. All right. Now what I'm going to do is I'm going to simply, so we're going to say, I'm going to delete that. Okay. And then I'll add, but I'm going to put it in a different zip code. Okay. All right. Now if I go to ping Bob to ping Larry again, I'm not going to be able to talk to Larry now. Again, this just goes back. This is the simplest of network demonstrations I can give. Again, now that Bob is not talking to Larry in the same zip code, I can't communicate to Mr. Larry, nor can Larry. All right. Well, let me give them the right address in here. Nor can Larry communicate with me now. All right, because I put it in a completely different zip code. Now, if I were to come over here, and we'll say, put Larry in that zip code now. Look at that. They can communicate it again. All right. That's as simple as a network design is, guys. All right. Computer to computer. Again, but it has to go back to addressing. Okay. Addressing is super important. All right. All right, guys. I'll probably, let me see, what time is it on my side of the world? It's about 7:30-ish. I've done, let me see, we've gone for about almost 2 hours. That's pretty good. I'll probably be back on probably shortly. Probably do some gaming and whatnot. But guys, tell me how this stream went. Tell me how if this, just tell me what you guys think. I'm gonna continue on doing it like this, guys, and hopefully I can get better at it. But guys, I'm looking for feedback. I'm looking for anything you guys can tell me. As always, this is a pleasure, guys. I love doing this stuff. All right, I love networking, guys. Yeah. So, without further ado, you guys have a good night. And like I said, I'll probably be on later if you guys are to game it up. And I have a couple of games I wanna start chiming into. But yeah, I'll see you in a little bit, guys. Ba-da-ba-ba, ba-da-ba-ba.